So should I begin?
Yes, please go ahead.
Okay. So first of all, thank you guys for inviting me, and happy birthday, Sasha. I took the liberty of changing the title a little bit, and sticking in a few things that I thought would be interesting to you guys. But I will start by talking, by giving a more transport and junctions oriented talk about full counting statistics. So, okay, so first of all, what is full counting statistics, and why do I find it interesting? So again, transport oriented, but if you think about a faucet with some water, and you have a very good faucet, it puts out a very consistent current, and you have some sort of device for measuring that current, and you measure the current coming out of the faucet as a function of time, you will probably get a quite boring result where that's constant. But if you have a better device, and you sort of zoom into the current, measure it at very high accuracy, even if you eliminate all sources of noise from the environment, right? If you have a perfect device and there are no trucks passing by, you will still have some noise as you measure the current as a function of time, just because the current is composed of molecules, which are a particulate matter. It's not really a uniform mass passing through your meter. At any given point, some number of molecules is passing through. So it's kind of interesting to measure this noise in the current. It tells you something about the properties of the current that you're measuring. And the first person to really take this seriously was Walter Schottky, who was thinking about vacuum tubes. And he had the electrons being released essentially randomly from a vacuum tube, and he was measuring a current that results from that. And that current had some noise in it, and you can do from a very simple classical argument, you can find, just by assuming that electrons are uncorrelated, that the ratio between the noise in the current, right, the variance of the current, and the current itself is actually the electron charge. So by measuring the noise of a current, you can tell something about the charge carriers of that current. Or in the case of these water molecules, you can tell if you're measuring a mass current of water, you can tell something about the mass of an individual molecule of water from this argument. So it's quite interesting, right? It's clear that this is information that isn't in just the current. You need the noise for that. And for quantum systems, actually, this very seminal paper by Levitok gave us an understanding of non-interacting transport. And you can write something like a modified Landauer formula for current noise. And even we have no interactions, just have non-interacting fermions. It turns out that you get a result which is somewhat different from the classical result, except at the limit where transmission goes to zero. And all this stuff is, I think, quite well understood by now. But for interacting systems, we actually don't know as much. In a way, there are more experiments than theory, at least out of equilibrium. So again, transport motivation, but if you measure current through a carbon nanotube, and you measure the noise to that current, and you plot, right, with a little bit of detail neglected, you plot something like the noise as a function of the current while varying the voltage. So you get a sequence of currents and noises. At one physical regime, you actually have an analytical result that comes from Fermi liquid theory, which tells you that this ratio should be something like 1.7, should be 5/3. And everywhere else, you don't really have a good theory for this. And this was something that motivated us. I'm not actually going to present results for this particular parameter regime, But it's quite interesting that everywhere on this graph, except at one point, basically the slope at zero temperature, zero bias, where Fermi liquid theory is valid, you don't have a theoretical result. And we wanted to address that to some degree. Now, you can go beyond just current and noise. So current is the first moment of something, noise is the second moment of something, and that something is a distribution. You can get all the moments, or you can get a generating function for that distribution. And if you write down a generating function for, say, the change in population in some part of the system, or anything you would like, then from that generating function, which has some sort of counting field, you can take derivatives with respect to the counting field at the limit where the counting field goes to zero and extract all the moments. That gives you a lot of information about what's going on. So why is that interesting? Let's look at another classical argument. You guys may have heard of this bus problem. If you use buses, I guess most of you are Europeans, not Americans, so you actually do use buses. So suppose your town has a circular road around it, and it takes time big T to make to go around it, right, all the way around it. You might think that if you put two buses on this route, then the maximum time that you would have to wait for a bus would be T over 2, or the average time that you would wait for a bus at least, right? Well, if you just miss a bus, then the average time you would wait for a bus, you would expect to be T over 2. But in practice, if you've ever done this in reality, you know that you wait for a really long time and then two buses come right after each other. And actually what happens is that a bus comes to the station, it picks up some people, it waits there as it's picking them up, and then when the next bus comes along, there are fewer people to pick up, so it waits a slightly shorter time. And because the first bus was delayed, when it gets to this next stop, there are a few more people to pick up. So it spends more time picking them up. And then the second bus catches up to it a little bit more, and it has even fewer people to pick up. So there turns out to be, right, in physics language, you would say there's an effective attractive interaction between buses mediated by the loading and unloading of passengers. And what happens eventually is that the buses bunch together. So if you look at the probability of having a bus come along sometime after you just missed a bus, you will probably still get a spike at T over 2, but you will probably get a larger spike at T. And it's interesting to investigate this distribution. And this is the kind of information that you can get out of full counting statistics, the time that you should expect for the first or second or nth bus to arrive. Okay, so again, this is classical, but you would want to do this for quantum systems. If you want a more a motivation that is more closely aligned to correlated solids, like correlated dynamics in solids, then there are really cool experiments in ultra-cold atoms, imitation of correlated solids, where they measure the number of fake electrons in, say, the left half of the lattice. And they measure the counting statistics for that quantity. Or you can pick an order parameter, something like a ferromagnetic or anti-ferromagnetic order parameter, and measure the counting statistics for that. And you can get a lot of information out of that. It's very interesting. There's great theory for that, even for non-interacting systems in equilibrium, but there's very little work done for dynamics and out of equilibrium. Okay, so what I mostly deal in is impurity models. So when I think of an impurity model, again, in this transport context, I usually have it coupled to multiple baths, or I might have a time-dependent field coupled to it. But essentially, I have a small interacting part coupled to the non-interacting parts. This is the Anderson impurity model, which you guys are familiar with. And if you try to solve this, right, there are many methods to solve this, but if you try to do it in Monte Carlo, and you actually want to do real-time dynamics, then you will have to do an expansion of a propagator, a real-time propagator. And that is a very dumb way of doing Monte Carlo usually, because it gets you to sign problems that you wouldn't have if you're doing it in imaginary time. But if you are interested in dynamics, you don't have much of a choice. And the way this sign problem looks, right, the way all sign problems look at the end is that you get an exponent in the error. So if I start my impurity model in some state, in this case, I start it, it's an Anderson impurity model. The atomic site has 4 possible states, and the unoccupied has 1 electron of up or down spin, or it can have 2 electrons in it. So I start it occupied by an up electron, and at time 0, I couple it to the back. I let it evolve in time. As I do this, I can track the populations of the 4 different states as a function of time. And when I do Monte Carlo, I will get a correct result. But after a short time, I'm going to get noise. And then I'm going to get really horrible noise, and my data becomes garbage. So to analyze this, what I can do is I can plot the magnitude of the noise as a function of time on a logarithmic scale. And I will get a straight line, which is an exponent. So this exponent is a sign problem. So what we proposed a few years ago is an algorithm called Inchworm Monte Carlo, which gets around this sign problem in a lot of cases. And the noise does generally increase with time, but it increases in some way which we think is a polynomial. That allows you to do Monte Carlo for real time. Essentially, it bypasses the sign problem, or at least part of this parameter space. So how does this work? The first Inchworm calculation, the first Inchworm algorithm that we wrote was a hybridization expansion, just like the non-crossing approximation, just like continuous time hybridization expansion Monte Carlo. So you start at the atomic limit, and you expand in the hybridization between your impurity and your bath. And you get a perturbation series. Then you write the objects in this perturbation series diagrammatically. So a propagator, E2IHT, either in imaginary time or in real time along the Keldysh contour, it doesn't really matter, it is a thick line. A thin line is a non-interacting propagator. It's not really non-interacting, it's an atomic limit propagator. E2IH0T, where H0 doesn't contain the hybridization. And this is a V, okay, an interaction vertex, which in this case is a hybridization event. So here an electron is passing between the dots and the path. And then you have these hybridization diagrams, which I think many of you are familiar with. And you can write the exact propagator in terms of an infinite sum of all possible hybridization diagrams. And if you sum these up with Monte Carlo, you will get the right results up to statistical error. So that's the hybridization expansion in a nutshell. And eventually that results in sign problems if you do it in real time, but often also in imaginary time. In Inchworm, we do it a little bit differently. We express a long propagator in terms of shorter propagators. So if you suppose for a moment that I want a propagator over this time interval, and this horizontal direction is time, and I know all propagators between time endpoints to the left of this arrow, between the beginning of time and the left of and this arrow. Okay, so I can write an expansion where the 0th order term is something like this. And what that is actually all possible hybridization lines that exist to the left of this arrow. Then, of course, that's not correct because I don't have any hybridization lines to the right. So I have to add hybridization lines which are to the right of the arrow. But if this time interval is short, there won't be that many of them. Then that's still not enough because I need to add hybridization lines that cross between these 2 intervals that go across the arrow. And then even that is not enough because it turns out that if I add a hybridization like that, I cut the propagator at this point. So here I will have a propagator from here to here, another propagator from here to here, and another one from here to here. So I don't have hybridization lines going from this interval to this interval. So I have to add those. And And I can continue that argument, so I'll have to add a hybridization line that crosses this hybridization line, for instance. But I don't have to sum any diagrams where I have inclusions fully inside this dressed part of the propagator, even if they also have other inclusions that would themselves be summed otherwise. And even if inclusions inside the dressed part include crossings. So you can come up with a pretty simple diagrammatic rule for which diagrams need to be summed, and which ones don't. And if I say that briefly in words, you only need diagrams where every hybridization line is in a cluster connected by crossing. This is a cluster connected by crossing, with at least one endpoint to the right of the arrow. Okay, so that's a rule. You can use a simple graph theory algorithm to see whether a particular hybridization expansion diagram obeys that. And if you sum up all diagrams that obey that rule, we call them Inchworm proper diagrams, you will get a formally exact expression for the propagator of the entire contour that recycles information about shorter time propagators that somehow you have. So what is somehow? The algorithm includes a process called inching. So first we sum up short propagators. That's easy. You just use regular Monte Carlo, right? Brute force their hybridization expansion Monte Carlo. Then you start extending them so they're longer and longer, and eventually you have long propagators. And we have some arguments as to why this helps, at least in some cases, bypass the sign problem, and in what cases it will no longer help, which I won't go into today. So that is the hybridization expansion Inchworm algorithm in a nutshell. Okay, now I want to show you some applications. So first, some applications to full counting statistics in transport. We evaluated this generating function, which I mentioned earlier. It's a generating function for a dot coupled to two leads. And I look at all moments of the population in the left lead. And I can do this with or without a voltage bias applied across the system. And here I do it for the non-interacting case. Non-interacting case is not so easy to solve with a hybridization expansion, right? Like just NCA, for instance, is quite bad for it. But with Monte Carlo, we should get an exact result. And here we see that we reproduce the generalized Levitov-Lesovic result for the non-interacting case, which gives us some, other than some small numerical errors, this gives us confidence that this actually works. And it's quite hard to read this generating functional. What you really want to look at is the moments or probability distributions. So here's a nice example. This is something you can extract from the generating functional. It's called a waiting time distribution. And this you can think of as the probability distribution for the first electron transfer event as a function of time. And you can do this on top. We do it for an equilibrium situation where we don't have a voltage bias. On the bottom, we have a voltage bias. And we do it for different initial conditions of the dot. Without a voltage bias, you have a left lead and a right lead. So if you integrate over this thing, at long times it will go to about 0.5. It's possible that the number of electrons in the left lead will actually never change. Why? Because it's possible that the only interaction that will ever occur is with the right lead. And your system is essentially two equilibrium leads coupled to a really small region that isn't in equilibrium with them. And you don't expect to have much happening, actually, in terms of charge transfer. If you turn on a voltage, then always some transport events will happen because you will have electrons constantly flowing from the left lead to the right lead. Now, if you start out in a charged state, okay, a spinless state, either the fully occupied or unoccupied initial condition, then you will have that first event occurring at a pretty short time. And then after that, nothing more will happen. But if you start in a magnetized initial condition, and you're pretty close to the Kondo regime, then you know that your system likes to stabilize a local moment, right? This we know from equilibrium NRG calculations many years ago. So what happens is that your waiting time distribution develops a long tail. And you can see that long tail in the integral. Right? It takes a very, very long time to reach the final point. And if you just increase the temperature to knock yourself out of the Kondo regime, then that long tail will die out and you will go back to fast relaxation rates. So this is kind of interesting, right? You see the statistics of charge and spin relaxation after a quantum quench, which is coupling a dot to a bath. You can also look at the statistics of multi-electron transfer events. So here I plot the probability of having, in black, 0 electrons, right? Of having the change in population of the left lead as a function of time be 0. Okay, at time 0, that's 1. And then I'm applying a voltage bias here, so that very quickly goes to 0. And here, the dashed lines are non-interacting, and the solid lines are with a pretty strong interaction. Now I can plot the same quantity for having 1 charge, right? The change in number of electrons of the left lead being +1, or sorry, 1 electron has left the left lead as a function of time. And you can see that that starts at 0, because at 0, nothing is left of the left lead, and then it peaks after some time. And you can do the same for 2, 3, 4, 5, 6, and so on electrons. And what you might notice is that at the first electron, actually the peak appears pretty much at the same place that the non-interacting peak appears. But for the second electron, it's shifted forward in time. Because once you have 1 electron going into the dot, then it will repel the second electron in many cases, right? Of course, it depends which process you have. You can have co-tunneling or sequential tunneling, and these things appear differently. But in the probability distribution, you can see this effect. And what you can do now is look at where these peaks appear as a function of the number of electrons. And you can do this for the non-interacting case and for the interacting case. This will give you a time scale. And this is something like the time between electron tunneling events between the lead and the dot. And in the non-interacting case, that time scale should be 1 in units of the inverse dot back coupling. That's the only energy scale you really, or time scale that you really have in the system. So you can't really get anything else. But in the interacting case, you see that it is actually going up. So the time between electron tunneling events goes up. And this makes sense physically because electrons repel each other. Right? So if we were thinking about the buses earlier, the buses have an interactive interaction between them, so they bunch together. Electrons will anti-bunch because Coulomb interaction will push them apart. And it's interesting that you can see this really at a single electron level here. The properties of the distribution of single electron tunneling events. Okay, so this is really what I wanted to say about full counting statistics. I won't go more into this, even though we've done a lot of other projects about this, but they're really transport oriented. I do think that this is an interesting concept also in the study of materials. Okay, so now I want to say something briefly. Right, I actually have, so I have 15 minutes, including questions, right?
Yes.
Yeah, okay. So I want to say something about a few of our projects that I think are maybe more thematically related to this conference, even though they don't all contain Inchworm yet, right? So to go from impurity models to lattices, you do DMFT, of course, and I don't really need to explain it here. But well, what does Inchworm actually offer us here? So first of all, even in equilibrium, some problems are actually hard. So Sasha was discussing how you know, even with the old Hirsch-Phi Monte Carlo, we could do actually 5 or 7 impurity problems. But on the other hand, you can find two impurity problems, like Martin was just showing, which are actually incredibly hard even in equilibrium. It's not very difficult to construct these things. In fact, if you look at multi-orbital models of EG orbitals in real materials, you will often have to actually either have a very special symmetry or to neglect something in order to not have a model like that. So essentially, the property that you need to have in order to have sign problems usually is some sort of non-diagonal hybridization between the different orbitals. And the standard imaginary time, continuous time hybridization expansions have trouble with models like that. They develop a sign problem, but instead of in time, there's no time, they develop it in imaginary time, or something like an inverse temperature. So what happens is that if you plot now an imaginary time Green's function, g of tau, this is essentially a two-site Kanamori model with some non-diagonal hybridization. And you do that with standard ALPS CT-HIB at a sequence of temperatures, increasing beta. And I do this for two slightly different models. One of these is the standard model that you would use in DMFT, that's on the right. This is essentially what CT-HIB was written for. And on the left, I have a model which just replaces the bath by essentially a couple of sites. So it's a discrete model, and I can solve it exactly by exact diagonalization very easily. You can get the exact Green's function. And I do this with CT-HIB and with Inchworm, and you get the same results at high temperature. As you go a little bit lower in temperature, CT-HIB starts to develop some noise. Inchworm also does, but it's much less noticeable. And typically, at some inverse temperature, CT-HIB will just break down. So an analysis that you can do, which I won't show here, is that the increase of noise with inverse temperature in CT-HIB is usually exponential eventually, once you have a sign problem. I would argue that that's what it means to have a sign problem. And in Inchworm, it is not. So you have an increase in the noise, but it does not appear to be exponential as far as we can tell. We can go to very low temperatures without breaking down. And this is demonstrated in a recent paper. Now, again, this is not dynamics or non-equilibrium, it's equilibrium statics because it's imaginary time. But I should say, right, that once we show that we don't really get a new sign problem here, then it seems that other than essentially technical difficulties and polynomial level complexities, we can actually also do this for non-equilibrium systems. It doesn't mean that it's easy, but it's not exponential, right? So it's a hard computational problem in the sense that classical hydrodynamics is a hard computational problem, right? You have polynomial factors that you have to deal with, but you don't break down exponentially. You don't give up. You don't need a quantum computer in order to solve interesting problems. So I think this is quite nice. I think it will be a few years before we can do something like what Martin was showing, not with perturbative results, but really with numerically exact impurity solvers. But I think that eventually we will get there. We can also do dynamical mean field theory in real time. This remains a lot harder than doing it in imaginary time. So this is just a single site Anderson impurity model doing DMFT. But you don't have any sort of analytical continuation here. And that is a big advantage. This means that you really have a way of controlling accuracy, again, with polynomial scaling. And again, it's not easy to do this for multi-orbital models. It's not easy to do this with non-equilibrium driving, but it's all polynomial factors, right? So essentially, it's possible. It seems like it's possible. So here's something that we did. Really, this was mostly perturbative. So this paper uses Inchworm only in the sense that we check that OCA makes sense. Most of the results are really calculated with OCA. But we thought in this collaboration with Emmanuel Google about a material, a Mott insulator, that is weakly coupled to a metallic bath. And then it turns out that you can quite easily move your material between essentially the insulating phase and a metallic phase, where you can see the spectral functions that characterize these things. Right? The metallic phase is the Kondo peak-driven phase. Right? It has this quasi-particle peak, which has to do with correlated electrons, with Kondo physics. So you can drive that by changing the coupling strength to the metal. So this is a proximity effect that controls the phase transition. How would you control a coupling to a metal? Well, you could think about a thin layer of strongly correlated material on top of an oxide or insulator on top of a metal. And then the tunneling rate between that is this, between these things is this lambda. That depends exponentially on the thickness of the insulating layer. So now you could take your system and squeeze it. You could put a capacitor on both sides of it and squeeze it in order to compress it. Then you could change lambda. You don't need to change it very much. So you can see that lambda has to be changed by maybe a few percent to go between these phases. But lambda depends exponentially on the displacement, right, on the compression that you apply to the material. So there's a hope that if the small change in compression, which means not a great amount of force or energy is dissipated here, would be able to change the tunneling rate significantly. And then you could maybe have some sort of device, right, experiment that controls this thing. And then you can do all sorts of things with that. One thing that I think is pretty cool is ultrafast switching. So you could actually sit in this coexistence regime, in the part of the phase transition in lambda, where you could be in either phase, depending on the history of your system. So this is a hysteresis loop. And if you sit there, you can apply a pulse of voltage to your capacitor, or a compression or decompression pulse. Essentially, you keep it at some voltage so that you can, by changing the voltage, you can either decompress it or compress it. And then if you compress it, thereby increasing lambda, you can actually take a system that was in an insulating phase and drive it into the metallic phase. And it's actually quite easier to do the other thing. You can start from the metallic phase, and by applying a decompression pulse, decreasing lambda, you can drive it into the insulating phase. It's harder to go to the metallic regime. It takes more time. At least that's what we predict. And again, you have to remember that this is OCA. But this dynamics, right, if you stick in parameters which might be relevant to solid state systems, right, to real Mott insulators, these timescales would be around femtoseconds or maybe tens of femtoseconds. So this is rather fast, and it's interesting, right? You keep the system always in the coexistence regime, and by short pulses, you can change its state so that it hysteretically remembers where it used to be. And we show that with a few extra assumptions, you can actually keep this thing, you can actually make some sort of memristor out of this, some sort of single terminal device that is like an electronic neuron based on a single crystal Mott insulator. Another project in which Sasha is also involved is in which is very much motivated by work from Martin, who has done a lot of groundbreaking stuff in this field. Is if we think about a Mott insulator, again, coupled weakly to a metal, and again, this is a very unrealistic model. We have a Bethe lattice, and every site is coupled to a bath, to a different metallic bath. and we apply an electric field, an oscillating electric field along some direction in the lattice. We define some sort of direction.
Guy, I'm sorry, you have 5 minutes, including questions.
Okay, so I'll take 2 minutes to finish up and then we'll do questions. Okay, so for this model, what we looked at is the energy current between your interacting lattice and your non-interacting paths. And you're applying an oscillating electric field, so that is oscillating. And if you don't apply a field, then okay, that is just zero. You're not driving anything. If you apply a weak field, that starts to go up. But then, interestingly, it starts to go down again. And sometimes it goes essentially almost to zero. And you can track the magnitude of this current as a function of the amplitude of the driving field. And you can see that there are special values where you have essentially no energy transport between your lattice and your bath. And you can understand this from a simple theory that's again related to something that Martin mentioned. So you can do essentially, well, okay, I won't go into that, but this is essentially a transformation plus a master equation. And again, this is all NCA. So I'm not sure whether it's correct, but in principle, there's no reason why we should be able to solve an exact, if somewhat unrealistic model of this and see whether you can really have a system which is driven but doesn't dissipate energy, which is quite a surprising result, I think. Also, I should mention that you might think that it's just going to some effective equilibrium state, but really, if you look at the population distribution of this system, at that state where it's not dissipating energy, then it's very much not in equilibrium. It's very different from a Fermi function. And you are clearly in a non-equilibrium state that is time-dependent, that is driven by an external power source, and where the bath is actually dissipating energy, but there is no transport of energy, at least on average, between the system and the bath. Okay, so I'll just put this up, and I guess we'll go to questions.